Okay, so today I want to start with a little bit of review. What we're going to get to eventually is solving equations that have like an x in them, and instead of giving you two sides like this, we would instead give you two sides like this. And it adds a whole nother set of complications into it first. So one thing at a time, let's make sure you still remember how to do this kind. That was the simplest kind. The next step we did was we put like cosine on the outside of something like that, and then you just had to do them from the inside out. Okay, so we'll do one on each of those kinds. But for right now, this one isn't a very good one because you wouldn't be able to do 1 and 3. They're not two sides of a triangle that you know. But if I did this, 1 over root 2, that is two sides of a triangle that you know. All right, so first step, rewrite that guy as a normal trig problem. Not an inverse, but a normal one. Sine of theta equals 1 over root 2. And that reminds you that you are looking for an angle. You already have the sides. So, what angle is it? Shouldn't there be two angles that work? No, because we've got that new thing that I gave you the second day after learning this, as that only from here to here can you have inverse sine. And only same area is where inverse tan can go. In cosine's the oddball, and that's from here to here. Nope. You would think so, but it's not. All right, so using that, where can I be? Because we're an inverse sine problem, really. We can only be in these two quadrants, there or there. We cannot be in the other two. So I'm going to draw myself a picture, and right off the bat, I'm eliminating this and this, because those are not allowed. Otherwise, there would have been another answer over here in this area, but it's not allowed. All right, so where should the triangle be? Right there, because sine is positive, and if sine was negative, I'd be down here. But sine's not negative, it's positive. So therefore, I'm in this spot, and the sine is opposite of our hypotenuse. There's 1, there's root 2. Do you get that we're in a 45 degree, 45, 90? Therefore, the answer is 45. And if they want it in radians, you would not use 45, you would use pi over 4. Raise your hand if you had that exactly right. Okay, awesome. Now, if the problem had been the same exact thing, except it had had a cosine of, like this out in front of it, I would still have had to start the problem exactly this way, and I still would have got pi over 4. I'm just going to save you the time. So now you're not going to have to do the inside because you just did it. But if the problem had a cosine out in front, what would we have to do now? Cosine of pi over 4. Because this whole thing right in here simplified down to pi over 4. So it's really cosine of pi over 4 now. So for cosine of pi over 4, that is as simple as it seems. You just have to figure out where's a triangle that would work for that. And am I allowed to go back into those other areas? No, because this only had one answer. All right, so cosine of pi over 4 is the 45, and so cosine of 45, it's a 1 square root of 2. Cosine's adjacent to hypotenuse, 1 over root 2. Does that mean that in this case, the cosine and the sine would have actually canceled each other at the beginning? Because the answer came out to that. But do we know that that's going to happen? No. So bottom line, sometimes those are going to cancel, but never just go like this. Because you might go, oh, cancel, cancel. I think the answer is going to be 1/5. Because there's a lot of times when the shortcut does not work and you get trampled by the bull. Okay. So let's actually do this one. Sine of inverse sine of 1/5. And let me show you why the answer is not 1/5. Try it. Start on the inside. Just start on the inside. Did you start on the inside and say sine of theta equals 1/5, and then did that bother you a little bit? I hope it did. Because sine's opposite over hypotenuse. Oh, wait a minute. Okay, it should bother you just because you don't know the triangle that goes with it, right? Okay. All right. I actually didn't do this problem the way I wanted to, so I'm sorry. I'm going to ask you to just erase one thing and flip it. I didn't want 1/5. I wanted 5/1. Because these are really tricky to make it so that it won't work. And I think the other one might have worked, but it would have involved finding a strange angle that you wouldn't have known how to do in your head. And so I'd rather just change the problem to this. And then you go like this, sine of theta equals 5/1. And now that should annoy you for a different reason. Not because you don't know which triangle you're in, but why? The hypotenuse is the small one, and that's not right. And in fact, specifically, there's a side on here that is bigger than the hypotenuse, and that is not just annoying, it's impossible. Therefore, what's the answer to this? Undefined or no solution. I'd prefer no solution because we don't have a 0 on the bottom, so we don't really want to call it undefined. Here's a shortcut for it I'm fine with. 0 with a slash through it. This is why you don't go like this. Oh, these two cancel. Sometimes they will. But this time it would not have worked. You'd have thought the answer was 5, and it wasn't. There was no solution. All right. Next one. Let's get into the new stuff for today then. The new stuff for today has two parts to it. One is kind of graphing-like, and I'm going to start with that. You're supposed to be able to know, if I asked you to graph sine of X, by now I'm hoping that that's like a, oh yeah, that's really easy, right? Okay. Everybody just graph sine of X quick and label the 4 spots along the x-axis that you're supposed to know, and label 2 spots on the y that you're supposed to know, and it should be zip zip easy. Because then I'll show you how you can use that knowledge to help you with the new function we have to know the graph of. What you're graphing right now is sine. I'm going to show you how to graph inverse sine. So here's your 4 spots. 2 pi, pi over 2, and 3 pi over 2. Then it goes up to 1 and down to -1. Raise your hand if you had that one right. Okay, good. So what's inverse sine look like? Do you remember that on inverses, when we created inverses, it was a thing where we would flip the x and the y around. Remember that? The x and y got reversed when we created inverses. There was a 3-step process. First thing, we changed f of x to y. Second step was to change the x and the y and reverse them. Well, that's what happens on inverses, is your x becomes your y and your y becomes your x. So the first thing you should do is draw to graph inverse sine. That's what we're trying to do now. This was sine. But what's inverse sine look like? You make your x and y and flip the x and the y around, but here's the part that you probably wouldn't have thought of. When you graph sine, I know you know that I could keep going, right? I could just keep going with this to the left and keep going forever in both directions, okay? When you graph sine, there's only one area of sine that's close to the origin and can be reflected over this line. That's what y, this is the line y equals x, and it has to be able to reflect over that line to be able to be an inverse. So, moral of the story is, we can only graph between here and here because that's the only area where when we do the inverse to it, that sines, it'll pass the vertical and horizontal line test. Now, I'm giving you all kinds of crap you don't have to know, but if you're wondering why are you only going to graph part of sine, it's because do you get in this little zone right here that I'm going to make green that this passes both the vertical and the horizontal line test? So that means in that little zone, it has an inverse that's also a function. Do you remember how if it doesn't pass the vertical and horizontal line test, then that means its function, its inverse can't be a function? So we only want to graph this function. So if we're going to graph this function, we can only do it between negative pi over 2 and pi over 2. Remember me saying that was important for inverse sine, is that it only went between negative pi over 2 and pi over 2? All right. Some of this is coming together for some of you that understand it at a little higher level, but all right, so I'm going to erase this part of my graph, and only this part of sine am I going to consider flipping. Now, how do I graph inverse sine? My y becomes my x, and my x becomes my y. My y used to be labeled with -1 and 1, so that means my x now has to be labeled with -1 and 1. Everybody go ahead and graph that on your, put that on your axes. You get how the y's just became the x's? And of course now, whatever used to be the x's will now become the y's. These were my things that were my x numbers. The numbering on the x-axis was negative pi over 2 and pi over 2. So that's going to become pi over 2 and negative pi over 2. Now the last thing, you may remember when we graphed cosecant that we would graph a helper function. We'd graph sine first, and then once we graphed sine first, we just made cosecant ride on the back of sine. I'm going to graph normal sine first, and normal sine would go like that. That's how sine normally looks. I'm going to use that just as a helper for myself. Inverses are a flip over the line y equals x, because that's changing the x for the y and the y for the x. So, final answer, there is your graph of inverse sine. For those of you that don't understand all that stuff about flipping it over the line y equals x, and why did you change the x and the y axis around? It's because it's an inverse. You can just memorize it. You get that it looks a lot like tangent, except it's got different labels, vastly different labels. All right. One of those things you put a star by in your notes, because the night before the test, it would be smart to go back and look at that one again, because you need to know what inverse sine looks like. You also have to be able to do inverse cosine, and you also have to be able to do inverse tangent. 3 new parent functions. You won't have to do a lot with them. You'll just have to know how they look. So now that I've got this done, here's my graph of inverse sine. What is the domain of inverse sine? -1 to 1. Notice that was the range of regular sine. You know, on regular sine, it goes from -1 to 1. The range of regular sine becomes the domain of inverse sine. And how about, what's the range of inverse sine? That to that. That's your range. And these guys were your domain. It just stops. Okay. So if you were asked, what is the range of inverse sine? You know what I'd really ask myself? What is the domain of sine? But you got to be careful, because the right answer to what is the domain of sine is actually sine just keeps going on forever. So we'd normally say that you can keep going forever, but you have to be smart enough to know that only this part of the graph is used to create inverse sine. So this is the graph of sine, but we only use this part of it. So it goes from negative pi over 2 to pi over 2, and it goes from 1 to negative 1. So now if that's sine, and I said what was the domain of inverse sine, I would actually be looking for the range of sine. So what's the domain of inverse sine? From negative 1 to 1. What's the range of inverse sine? From that to that. Okay. Same thing's going to happen on cosine. So you better make a nice picture for your parent graph of cosine. I want to go make that go faster. Okay. Cosine starts, it's kind of like a big valley, right? Do you get if I do this, it won't pass the vertical and horizontal line tests? Only part of this will pass both the vertical and horizontal line tests. If I cut that out, do you get it will pass the vertical and horizontal line tests? So that's the part of cosine that I'm going to use. And that goes from 0 to pi. It's not the best picture in the world. I'm going to try just to do a little better job. There. This is regular cosine now. But it's actually more important to understand what part of regular cosine we use, because then we could just flip it. So here's from 1 to negative 1. Do you get that that's part of cosine? That's the part we use to make inverse cosine. So regular cosine, in this picture I have just drawn you, the domain is from here to here. So that creates the what of the other function. That makes the range of the other function from 0 to pi. So here's my other function. It goes from 0 to pi. And why did I go that way? Because you switch. Your x's become your y's. So here's my inverse cosine graph I'm building for you. And its domain here has to come from the range of the other one. The range of this one was from 1 to negative 1. Negative 1 to 1. And then to actually make the picture, this one gets weird, because you flip it over this line, and it kind of goes I better do it one point at a time. You're not going to be asked to draw a picture of inverse cosine, but 0, 1 becomes 1, 0. So it will go through that spot right there. This spot here becomes this spot here. That is at pi over 2 comma 0, so it's going to become 0 comma pi over 2, which would be right there. It would go through that spot right there. And it goes something like that once it is flipped across that line. That's pretty close, actually. It's not bad. Okay. So now, what would I ask you about inverse cosine? What's the domain and range of inverse cosine? And so what you should ask yourself is, what's the domain and range of regular cosine? This part of it. And then we just have to flip them. So what is the domain of inverse cosine? The domain of inverse cosine is from negative 1 to 1. And it comes from the range of the regular one, see? And what is the domain, or the range of inverse cosine? 0 to pi. These two make the range, those two make the domain. Last one's tangent. Inverse tangent is based, of course, on tangent. So let's look at tangent first. Here's your base tangent graph. And the nice thing about tangent is the tangent can flip just right off the bat. We don't have to, like, only take part of it. Tangent goes like this. right? That's your basic tangent graph. It goes from negative pi over 2 to pi over 2. Remember that one? Okay. Now, let me ask you, what are the domain and range of tangent? What's the domain of tangent? Negative pi over 2 to pi over 2. What's the range of regular tangent? Negative infinity to positive infinity. So if I asked you for inverse tangent, what's the domain and range? Inverse tangent's domain and range are just the reverse. Inverse tangent's domain is whatever we said for the range. So that's this right here. And it becomes negative infinity to infinity. The range comes from the domain. Negative pi over 2 to pi over 2. Those are all parentheses, by the way, no brackets. Because tangent can't touch those asymptote lines, right? And tangent will never get to negative infinity or positive infinity, so those are all parentheses. No, because on cosine and sine you can touch 1 and you can touch negative 1, right? So those are brackets on those. All right. That's just some stuff you got to write in your notes and try to remember that, okay, for the inverse, the x and y switch. So the range of the one becomes the domain of the other. Question? Yes. So now what I have to do is flip it over this line y equals x. The tangent starts looking weird. If I flip that, it goes like this. And do you get that this, whatever was on the x-axis becomes the y-axis? And whatever was on the y-axis, which was, there were no labels. Why? Because it goes forever on the y-axis. So we don't need to label the y-axis. Sorry, we didn't need to label the y-axis on the original, so we don't need to label the x-axis here on the graph of inverse tan. But like I said, what you need to focus on is being able to handle what are the range and domain of these. So you need to know the domain and range of the originals so you can flip them. All right, that's about half of what you need to know. Here's the other half. The other half is where I was telling you, I give you like a little preview so your subconscious could start working on it. If you're asked to do a inverse problem, except they don't give you the sides, they just give you like an x. Here's an example of one. Go back to basic themes I've told you the whole time. How do you start a problem like this? Inside. When you start with the inside, you want to write it like a way you're more familiar with, right? So, what's a way to write this more normally? Sine of theta equals x, and I have always told you also to make it into two sides. So let's have two sides. X over 1. Now ask yourself, where should I draw this triangle? Remember, it's a triangle. Where should I draw that triangle? How about this? Where can't I draw the triangle? I can't draw it here and here because sine's only allowed from here to here. Inverse sine is. You get that? And yes, I'm going to start with putting it in the top right corner right here. Right there. And if sine is opposite over hypotenuse, what did I just give you for the opposite side? X. And the hypotenuse side? 1. Now, if I'm supposed to then use this triangle, I'm going to need that third side usually. because usually I'm going to have like cosine on the outside here. But in this case, I just have sine on the outside. So it's actually a pretty easy problem. Now that I've drawn this picture, what is the normal sine of that picture? X over 1. Sine is opposite of hypotenuse, right? So we weren't asked how big the angle was. They never asked me that because you couldn't figure it out because they never told you how big the other side was. What they asked you, what is the sine for that triangle that you'd make for this? So here's the triangle. What's the sine? X over 1. So the answer is x, or x over 1. X over 1 is the same exact thing as x. So that's equal to x. It's a good question. Do we have to say how big x is? No, they never told me how big x was. We're not talking about the angle here. We're not talking about the angle. But, oh, I see what you're saying. You're saying that it has to be bigger than, no, less than 1. Or bigger than 0. You do not have to say that. But that's a very good observation. I didn't even think of that. Because 1, if the hypotenuse is 1, x has to be smaller than that. That's a good point. You're thinking more than you even have to. All right. Let's do another one like that. Let's say we had 2 times the inverse sine of x is equal to 1. Two times the inverse sine of x is equal to 1. First thing, can we just treat this like an equation and this is like the big clump I'm supposed to be like solving for? Yes, we can. And you usually get that clump alone by getting rid of the 2. So how can I do that? Divide by 2. I'm going to divide both sides by 2. And then this will cancel this. And now I've got inverse sine of x is equal to 1/2. All right. Now, we better rewrite this thing as a way, something we're used to. Just keep on following the rules I've given you. So then I better write that as sine of theta has to equal x over 1. Because your sides, you always want to have 2 sides. Remember that? You never want to have just one side because you're going to make a triangle out of it. You need 2 sides. What happened to the 1/2? It's still there. I'm going to figure out what this is, and then I'm going to say it's equal to 1/2. First, I got to figure what that is. So if sine of theta is equal to x over 1, then what kind of a triangle could I draw for this thing? Sine is opposite of hypotenuse, right? So the opposite side is x, the hypotenuse side is 1. But wait a minute. That's got to equal 1/2. Look at this has to equal 1/2. The side ratio has to be 1/2. So what does x have to be equal to? It has to be half as big as this, right? So it's 1/2. It's okay. Don't worry. That was a hard problem. What you're supposed to be learning here is how to handle it when we don't tell you how long the sides are. And you've never had that problem before. So I get how that's going to be a challenge for you. All right. Let's do another one. How about this? I'm going to hand the worksheet out. We'll do some of these together. Get started on your homework. I'm going to pause for a second while we get the homework out. So here we go. On number 1, let's consider the domain and range of inverse sine. Well, if you took good notes, this part should be easy for you. What am I going to go back to? I'm going to go back to regular sine and figure out regular sine's domain and range, and then I'm just going to flip them. You do not want to just try to memorize the picture of inverse sine, because you'll forget what it looks like. But you'll probably remember what sine looks like. All we got to do is limit it to between negative pi over 2 and pi over 2, because that's the only part that passes the vertical and horizontal line tests and is close to 0. Okay, so now, where does it go from here to here? On the y-axis, what should I label it? 1 and negative 1. Okay, good. That's regular sine, and it's telling me its domain and range. The domain is these guys. So what does that become? The range of inverse sine. And that's from negative pi over 2 to pi over 2. And can sine get to those places? Yes, it can. So it should be brackets. Okay, and then the domain. The domain of inverse sine comes from the range of regular sine, and that's from here to here. So from negative 1 to 1. And does regular sine actually touch at 1 and negative 1? Yes, so it's brackets. Okay, so when you're doing the cosine and the tangent one, what I would do is, instead of doing the inverses, I'd do the regular functions. Figure out their domain and ranges, and then just flip them around. Domain will become the range, and the range will become the domain. All right, let's move on to problem 4. And by the way, this homework is a little bit long for the amount of time that we have, so I will be having you skip a few along the way here. But let's do number 4 together. Number 4 says inverse sine of 2x. What the heck do they want me to do with that? Let's read the directions. Use transformations to just describe how the graph is related to the basic inverse trig graph. So in other words, compared to the basic one, that 2 is the only thing that's doing something to the graph. What's it doing? Horizontal stretch, vertical shrink. I mean, horizontal what? Horizontal shrink. H shrink factor, don't say 2. Factor of a half. If it's shrinking, you got to use a decimal. Horizontal shrink with factor of a half. Okay. Then, what's domain and range of this squished inverse sine? Well, first I better figure out what the normal domain and range are. You want to copy that down from the problem above it on number 1? Problem number 1 had the normal domain and range of inverse sine. So what are the normal domain and range of inverse sine? Well, the domain comes from the range. The range of normal sine is from negative 1 to 1. And the range of normal sine, the range of inverse sine comes from the domain of regular sine. The domain of regular sine normally would be it goes forever, but we limit it to between negative pi over 2 and pi over 2. So hopefully you have these. You can get those. Those are the normal ones. But now we've got to do this. We've got to have a horizontal shrink of factor a half. Which does that affect? Its domain or its range? Domain. And it's going to be half as big as it used to be. So now it's going to go from negative a half to positive a half. That'll be going half as big as it used to be, right? All right, so you figure out what has been done to the function. This one had a horizontal shrink. Then you figure out what does that affect. Horizontal shrink is messing with the domain, and that means those numbers had to be half as big. Does that horizontal shrink affect the range at all? No. So the range is still negative pi over 2 to pi over 2. So there's your right answers for number 4. All right, you may skip number 7. And now we'll skip some more on the back here. Those are still fairly easy ones. You don't want to skip too many of the easy. You'd rather skip some of the hard ones instead. Let's go to number 8. Find the solution to the equation. If the answer is an angle, answer in radians. Okay, for number 8. Number 8 is sine of inverse sine of x. Equals 1. I'm going to just set that equals 1 aside for a while, and I'm going to remember that again later. But for right now, I'm going to focus on the inside. Mr. Servo said start on the inside, so I'm starting in there. And then I'm going to go sine of theta equals x over 1. And then that tells me I should draw a triangle with sides of x and 1. Here's my triangle with sides of x for the opposite and 1 for the hypotenuse. In case you wanted to know this third side, the third side is the square root of the other two sides, 1 squared minus x squared. Because this squared and this squared, it's the whole Pythagorean theorem thing. So you take the square root of the bigger side minus the smaller side, squared. All right, so anyway, if I ever needed that third side, which you will on a future problem. But right now, I don't even need that because I'm taking the sine within that triangle. Sine is the opposite over the hypotenuse, so it's just x over 1, so it's just x. Is this one of those cases where these would have canceled? Yup. So if those just cancel off, and the answer is just x over there, what's the final answer? X on this side, and what do I have on the right side? Equals 1. X equals 1. Yes, because if the hypotenuse and the opposite are the same, do you get that we will be on one of these guys, the quadrantals? So you'd actually be right there. They never asked you what the angle was, but that's where you would be. Okay, so we'll do another one like that. We had already done something like that. Number 8. Let's do like, I actually did 10 in class. Let's do, how about 12? Let's do 12 together. And you are, by the way, going to skip 11 and 13. Okay, number 12. Cosine of inverse cosine of x has to equal 1/3. All right, we'll start in the middle, starting right there. Cosine of some angle is equal to x. That's really over 1, right? Now I'm going to draw my little picture. What does that look like? If this is theta, and that's cosine, cosine's adjacent over hypotenuse, it's x here and 1, cosine's adjacent over hypotenuse. Yes, there we go, 1 there. And if I'm doing cosine within that same triangle now, cosine of that, it's going to be x over 1, it's going to be equal to x again. I had to do that check, though. I know you're going to be really tempted from now on to be just like, oh, so these just always cancel? Nope, they don't always cancel, but they do in that case. It came out to cosine of this triangle, which would be x over 1, which is x. So I just figured out that that whole side is just equal to x. What's the other side? X equals 1/3 then. This side came out to x. Therefore, x equals 1/3. All right, let's move down and try one like number 14. This is where the signs are, the functions are actually different. It's tangent on the inside and sine on the outside. All right, so number 14. But I bet you know where to start. Where do you start? In the middle. Okay, so first thought is take that, rewrite it some way you're more familiar with. Tangent of theta is equal to 1 over x. So, I'm wrong. Sorry. Tangent is x over 1. Can you draw a picture for that? Yes, you can. With all these ones with x, you can always draw a picture with a triangle. Because we don't know how long x is, so we just kind of draw the picture and we label it as x. We don't know how big it really is until later. Okay. Now, if opposite, tangent's opposite over adjacent, right? The opposite side is going to be there, if that's theta. Ugh, that's ugly theta, but that's all right. And adjacent is 1. That side, got to get good at making these fairly quick because you don't want to take forever on these problems. 1 squared plus x squared. Very good. Those two added, because that's the hypotenuse. That's the big boy. The other two added together make the hypotenuse. So 1 squared plus x squared, one underneath that square root sign. Why did I care about that? Because now I have to do sine within this triangle I just created, and I'll need the hypotenuse to be able to do sine, right? So sine is opposite over hypotenuse. If I did opposite over, if I hadn't ever figured that out, I wouldn't be able to answer the question. So sine is opposite over hypotenuse, otherwise known as x over square root of 1 squared is just 1, isn't it? 1 plus x squared. There's your answer. It's getting a little obscure, a little abstract, because it's got lots of... Your answer is this weird x over x thing, and it's hard to even understand what you have there. That's a ratio of sides. That's not an angle. That's a side ratio. And why don't we just have numbers? Because they never told us numbers. They told me the side was just x. So I have to have x in my answer. Yes, sir? Oh, I get what you're saying. You're thinking that I can take the square root of 1 plus x squared and say it's 1 plus x, but it is not. That's a common misunderstanding. You know, it's based on the same thing. 1 plus x quantity squared is not 1 plus x squared. Remember that one? Yep. It is the square root of 1 plus x squared. Are you trying to say you want to simplify that more, or? Oh, are you just asking about this little squared on the 1? Oh, that the only thing you care? You can have the 1 squared in there, or you can have 1 in there. But on the test, we always say your answer should be simplified as far as possible. Would you agree that 1 squared is probably not as simple as 1? That's all. It's just a little simplification thing, I guess. Yeah, that's just a 1. Okay. I know this is tough stuff. I get it. I get this is where the rubber meets the road. I hope you get that. And so whether or not you start to study, they were down to, I think there's only 2 trig tests left, and they're not going to be fun. If you study for them, you can be all right. But if you just cruise through like, you know, kind of act like business as usual, these are going to kick your butt because they're tough. The average score on one of these tests last year, where the average score is often like an A minus or a B plus, the average score was like a C minus average on one of these tests last year. But I have an idea for teaching it better this year, so I think it'll be better. But anyway, it's not easy. So don't give up. Try hard. Take good notes. Actually study your notes the night before the test. Remember I gave you a couple things I said to star this in your notes because you really want to know this? All right. Okay, so rest of the time is yours to work on your homework. If you need any help, come on up here and ask me.